Okay, gang. So now we know what our differential operators are. We know the ones we're familiar with. So let's move on to a new one. Let's talk about divergence. Let's open with a definition. So divergence is when a del operator operates on a vector field with a dot product, resulting in a scalar field. And I just want to quickly call our attention to the vector and scalar aspects of this. So when we're talking about divergence, it's important to remember that we have two vector inputs, and then of course we are dot producting them. So we are going to get a scalar output. And fun fact about this output here is that it is used to find flux through a surface or surfaces in 3D using divergence theorem. All right, so let's do a quick example of calculating our divergence. So let's start with this first guy. And what we are going to do here is dot product them. And here we're just, oh, this one is in just 2 dimensions. Starting us off nice and easy. And now we are seriously just going to add these guys together. These guys, and that is going to give us a result of 2x plus 1. So this tells us that our divergence only depends on x because that is the only variable we have here at the end. Okay, so let's do an example in 3D now. And I'm going to write this out here again. Right, and now we are just going to dot product this across and take our partial derivatives with respect to each of these variables, just like we did before. And that is going to give us 1 plus 2 plus 3, which equals 6. All right, and that means there's positive spreading everywhere. But what exactly do I mean by spreading? So let's dig ourselves a little bit deeper now that I've given us a mathematical base. And let's make sure we really, really conceptually understand what we're doing here with divergence. Okay, so one really great way to think about vector fields is to think of them as representing a fluid flow. What I mean by that is you can think of every single point in space as a particle, maybe an air particle or a water particle or something like that, because a vector field associates each point in space with some kind of vector, just like we see here and here, and we'll draw another one here. And even if they all aren't shown on a vector field, in reality, the vector field represents infinitely many points in space being associated with vectors. So um, we just want to remember that the vectors we see here are just a small representation of infinitely many vectors and points. Okay, so at any given instant, the velocity of one of these fluid particles is given by the vector connected to it. And as it moves, it will touch a different vector, causing its velocity to turn. So let's take this guy, for example. Let's say it's going along, this particle is going along, and he gets here, and all of a sudden we encounter this vector. So now we're going to turn, da-di-da, we're going along, we encounter this vector, we're going to turn, we're going to go this way, keep going, keep going. And that is kind of a rough representation of one of these trajectories might do. So let's take a look at another one of these. So we're going along, and now we've encountered this vector. We're going to keep going. Now I've got another one, another one. And so you can just see kind of the trajectory and the flow, if you will, of what we're choosing to represent this vector field as, so particles. Okay, now let's talk about this example. So in this example, we see all of these vectors, all these points, they're converging towards our origin here, our 0, comma 0. We've got all these points, and this is what we would call negative divergence. Or if we were to talk about a real world example, we would think about perhaps the drain in a sink, right? So if these were really all particles of or molecules of water, they would be heading down towards the drain, and they're all converging on this one point at the origin. Okay, now let's talk about an example of divergence or positive divergence. So when we think about divergence, usually we want to think about one specific region and how all of these particles, imagined particles or vectors, are moving or demonstrating movement in relation to this region. So when we think about the origin here, we are thinking about how all of these guys are moving in relation to it. And as we can see, every vector here is moving away from the origin, from our region of interest, if you will. And so we're going to call this positive divergence. And going back up to this example briefly, once again, we can see this is our region of focus around the origin, and all of these vectors are moving inward in relation to it. But for example, this would be an example of negative divergence around the origin. However, let's say we were talking about this region here, right? So we have vectors that are coming in, and we have vectors that are coming out. And all of these vectors are about the same length. They're about the same length. So particles are moving in and out at about the same speed. So this area here, we would actually say has zero divergence, right? There's not really a net change in how particles are moving in that region. So yeah, divergence equals 0. And another example of this could look like something like this. Anything where our net change would be 0. Actually, let's go back and do another example of what positive divergence or diverging away might look like, because that can look like a bunch of different things. Positive divergence could also be something along the lines of this. Let's say we're talking about this general region right here, and maybe we've got um, couple, some vectors showing some particles coming in. They're not very big, but what we've got here on the other side, we've got some way bigger vectors heading. So here, the amount that is moving out, amount going out, is greater than the amount going in. And so our net change basically is going to be, well, more is going out than is coming in. So we're going to call that positive divergence. And you could say the same thing about, well, the opposite thing about negative divergence here, right? So we've got some little guys, they're heading out, but we've got way bigger vectors coming in, right? And so we have more coming in than is going out. So we're going to call that negative divergence, even though there are some little guys heading out here. Let's go back to pink pen. Okay, so let's talk about how to remember that. Because when I think about this, I think positive, it's going away. When I think negative, it's coming in. That's kind of confusing to me. It seems a little counterintuitive. So the way that I like to think about it is that when you think about negative divergence, let's say that divergence was a homebody, somebody that doesn't really like to leave the house. They're happy at home. Now, for them, if more people started showing up to their house, now we've got more people coming in, that would be sad for this homebody. Give them a frowny face now, right? So we're going to imagine that divergence is a homebody, or we'll call them an introvert. So more people, which is really particles, is negative for them. So that is how we are going to remember that. Right, so let's talk about real world applications again. So again, another example of divergence, both positive and negative, would be a sink. So if we had uh, positive divergence, you might think about something like a faucet, right? So we have all this water coming out. It's gotta come out. And then we might think about negative divergence in a real world application as perhaps the drain in that sink. So all of our water is heading down that drain. It's all converging to that same point. And all of the water here is diverging away from that same point.